So we have today Chris Bettinger here, and he's working on edible electronics. And so besides, so there you have a lot of new materials you're working on, but what do you see as hot topics in materials research which has the most potential and impact in technology and industry in the moment?
Anke, thanks for having me. It's great to be here. So we work broadly in this relatively nascent field called edible electronics, and this is kind of a catch-all term that embodies the science and technology surrounding medical devices that you eat. And these are actually devices that have been around for quite a long time. And so you can think back to the early days of NASA when they were interested in monitoring the physiology of astronauts, ambulatory astronauts. So they embodied the idea of encapsulating sensors in pills and then deliver them orally. And so this is, like many things in science and engineering, not a new idea, but to your point, we've made advances in materials that now enable new kinds of modalities and have expanded the potential impact of this idea. So one example from our work is we think about batteries that are designed specifically to operate in the GI tract. And so these are substantially different from batteries that are designed for cell phones and for laptops, for grid-scale energy storage. And so we have essentially a new set of constraints that emerges from the location that these devices are intended to operate. And so we discovered that we can use melanin pigments, actually pigments in the skin and your hair and your eyes, as half of these kinds of batteries that operate in the GI tract.
I'm not getting very hungry about that. So how long does it take until it is digested then? In case?
Yeah, that's a great question. So the typical ingestible device will, the transit time depends on the size of the device. So let's say for an ingestible camera, it'll be typically on the order of 2 centimeters, a cylinder that's 2 centimeters long by 1 centimeter in diameter. And so a pill like that could take anywhere from 24 hours to sort of transit the GI tract.
Okay. Didn't have breakfast this morning. Okay, so giving the importance of innovation in industry, how is the role of applied and basic research, both inside and outside of companies, on this?
Yeah, so it's again, if I can speak just about this topic specifically, it's interesting because basically there are already products that are on the market. So they're actually fairly mature products, and they kind of adopted a certain kind of materials toolbox to enable that, right? And so it's interesting because we're kind of going back and sort of starting over and kind of rethinking these devices and asking the question, if these could be constructed in a more rational way, what would they be constructed of? How would they be fabricated? How can we use things like 3D printing to make new kinds of devices, new kinds of form factors? And so I think it's going to be, it's interesting because we have essentially basic science and mature products, and there's kind of this gap that emerges, this temporal gap that has emerged over the last, I would say, 15 years or so. And then this is specific to this type of medical device.
And the research, does it take place mainly in companies or in universities, or where do we have the breakthroughs?
Right. Yeah. So. Right. That's a great question. So a lot of the advances in, let's say, communication, microelectronics, packaging, actuators, those are actually done by companies because they have more resources, and they can also leverage their personnel and address potential regulatory challenges. They're always thinking about regulatory challenges as they're designing and manufacturing these devices. So those are, I would classify as engineering challenges. And then there's a new set of the science comes in terms of the materials and the fabrication, right? So what would be an ideal battery, to use in this application? So we have some that we can use. Are they optimal? Are they ideal? Are they holding that technology back? Could there be new ways of delivering therapies or diagnostics that would need new materials to enable those kinds of modalities, right? And then for sure in microfabrication is very fabrication. So the FDA approved the first 3D printed pill, I think over the summer of 2015. And so there's kind of this synergy of electronics and new materials and fabrication and custom implants and custom fabrication. So it's all kind of coming together at the same time, which makes it a pretty exciting and interdisciplinary effort.
And what's about alternatives like for energy delivery, like thermoelectrics locally also? So how would you deal with new technologies? For example, if you're talking about energy converters to be implemented in this, how would this take place? Is it on locations like this, on a conference that
Yeah.
you find new ideas, or
Yeah, that's right.
other trans-
Yeah, that's right. Actually, when we first embarked on this journey, we surveyed just the literature and thought about really every kind of power source. Let's just say power source. Like, what would you use? And so, if you kind of peel back the sort of the fog, so to speak, or if you peel back, some of the underlying issues with some of these technologies. Again, it's great science. It's a great sandbox to play in, so to speak. But we were interested in translating devices eventually, and so that's why we settled on batteries. But to your point about the excitement surrounding, there's all kinds of interesting piezoelectric generators and new kinds of antennas for electromagnetic energy transfer through the body, and so those are all fun scientific pursuits, and we keep track of them. But as a polymer engineer or polymer kind of chemist, we don't feel like we can contribute meaningfully in that space.
Okay. So, but you're pursuing this direction in polymeric materials and not inorganic materials.
Yeah, well, no, that's a great point. So, there are. I mean, it's really funny. People have this, I think, this notion that organic is biocompatible and inorganic is not, right? But you think about orthopedic implants and stents, right? Those are, we rely a lot on those kinds of materials. And one example that's very interesting is magnesium. So magnesium comes up a lot in terms of lightweight alloys, but it's also actually, you can oxidize it and it can dissolve. And there's actually a fair amount of magnesium, dissolved magnesium in all of our bodies right now. So that would be an example where you may not think intuitively to leverage the properties of magnesium, but in fact, it could be very useful.
Okay, very good. So thank you very much for this nice conversation, and